My name is Esteban. I work in the Google Brain team, where I lead a small group of people that do research on neuroarchitecture search using evolutionary algorithms. It's a term that I try to avoid. I think it works well to label a field as a whole when we all know what we're talking about. But to describe the field, I think it might be a little complicated. So I prefer more specific terms. For example, evolutionary computation or neural computation or something like this. Part of it is, I think, because if you were to ask me what's my definition of natural intelligence, I don't have that either. Right? I don't have it. Maybe psychologists do, but not me. So saying artificial intelligence conjures up a little bit of the feeling that it might be something like natural intelligence done by a computer, but that's not a very good description of it, probably. So when it's clear from context, I use it, otherwise I avoid it. Well, there are certainly connections between the two fields. Like, for example, if you look at retinal neuroscience, you can see, if you compare that with the image classification, for example, you can see a convolutional structure in both. And the other deeper connections, like the formalism of information theory, applies to both neuroscience and to computer science, machine learning, and so on. But these are just that. They are connections. It's not to the point that one field is driving the other one or anything like that. I think each of the two fields does makes progress based on their evidence and or practical needs of the field, and they might diverge because of this, and that's natural because the hardware is different, right? In the biological side, we have the brain, right? It's big. It has a lot of fan out, meaning one neuron can connect to 10,000 neurons. That's okay, and it's very slow compared to what a chip can do. The chip is small and flat. That means it can dissipate heat well. It can compute things really, really quickly. But because it's flat, it's hard to get the wires, many wires out from one point in the chip, so you can't have as much fan out. So if the hardware is so different, it's natural that the software might be different too. Yeah. And I think that's a little bit of why the two fields are maybe not as close as we might want or something. But I hope there will be more connections surfacing as we learn more. Yeah. Well, I've liked evolutionary computation for a long time. Like I remember in college, I took a biology class, and in order not to write a paper, I wrote a computer program and talked about it. It was my way to get out of the class requirement, but it was a lot of fun. And then I would find weird answers. So this was a program that did some simulated evolution, sort of like what we're doing now, but much more basic and with less of a goal. But the solutions were sometimes unexpected. And that was interesting. And then at a deeper level, or more seriously, it seems that a system with such simple rules, I mean, they're simple in outline. Of course, biology is very complex, yeah, and the understanding of evolution is very difficult. But at least the outline description of it is simple. And with such a simple process, you can generate an incredible amount of diversity, complexity, and that's just fascinating. Our goal was to show that evolutionary algorithms, which had been around for a long time, could be applied today to the same problem that machine learning researchers were working on and have good results, comparatively speaking. That was our overall theme of the last 2 or 3 years or so. So to do that, we wrote a couple papers, and in the last one we tried to compare evolution with reinforcement learning, and we were surprised that out of this comparison work, which was meant to be a dull, work to inform a little bit, and maybe it's still dull, but from it came models that actually managed to reach state of the art, or to set a new state of the art at the time. This field evolved, so maybe no longer. So I think to some extent we showed that you could use evolution today for the problems that researchers care about. That does not mean to say that evolution gives you an answer altogether. There's still a lot of things to be solved, and there are issues interpreting the results of evolution research, a lot of questions about the specificity of it, but it does give practical answers, as is shown by, for example, a state-of-the-art model. So it's worth exploring. Evolution surprised me a few times, yes. For one thing, the fact that a state-of-the-art model came out of it was a surprise. I wasn't expecting that, and I think my colleagues were not expecting that either. And so that was nice. But maybe the more fun surprises are smaller. Like, for example, sometimes, we would code a bug by accident. Yeah, we made a mistake in the code, and evolution finds ways to work around it, and that's kind of entertaining. For example, it might find other ways to achieve the same thing, and maybe we didn't notice there was a bug, and then we say, oh, there was a bug, but we didn't notice it because evolution was solving the problem for us. So that was a nice surprise, and another nice surprise, I wouldn't say nice surprise, another surprise was sometimes the things that come out of the evolutionary process are weird. So the traditional neural networks have this sort of pattern of putting a convolution and a rectification, and then a convolution and a rectification. And what we had from our experiments sometimes was a convolution and a rectification. And that is odd. And that might not be meaningful. So it might be that it's there just by chance. Yeah. But the cool thing about it is that the same thing happens in biology. For example, if you look at your eye, right, our eyes, you have the retina detecting light, and between the light source and the retina you have some blood vessels, and that's a weird thing. Like if you had designed it, if a designer might not have done it that way. It's a bit like designing a TV and having the cables droop over the screen, right? And so this sometimes accidents happen, and then again the pattern is the same. Evolution works around and makes it work anyway, and that happened both in the biology, right? For example, in the structure of our eye, not every eye, but our eye, and in the experiments, the artificial experiments too. I think evolutionary computation is a player, and reinforcement learning is another player in the field, and there are many others. And I don't want to seem that just because I happen to be studying evolutionary computation, I don't want to seem like I feel that that's the one. They're all good players, and they might have advantages over others depending on what you're using them for, as is natural to expect. And we'll see in time which ones work more for example, for discovering architectures, that's what we had been doing, discovering neural network architectures. But one thing that evolution has going for it is that it has proven to work. And of course, the artificial evolution is not the same as the natural evolution. Sometimes we try to make them more similar, sometimes we purposefully make them different. But in nature, evolution has managed to get great results. Not only intelligence, but kindness and creativity are also products of evolution. And these are things that we want in computer programs, right? So hopefully we can get them. I don't know. I think whenever it makes sense, we should take the influence, but we should be guided by wanting to do the same thing that biology does. Yeah. There may be practical advantages if there's a theory that is well formulated in biology, and we could, if we use a similar process, then we could apply that theory, then that sounds like a good reason. But just making it the same for the sake of making it the same doesn't seem to be the right thing to do, because the domains are different. Yeah? When you're involved in the architecture of a neural network, you don't have the same constraints that nature had for evolving the architecture of a brain or something like that. For example, the brain has to fit in a certain size, or the connection between the eye and the brain has to go through a certain gap. So, you know, you could say the brain has these limitations, we don't have these limitations, we have other limitations. Like how many flops can we do with this particular chip, and so on. It's hard to predict where it will go, but it's a little easier to think about what we need. And my hunch is that we need a broader understanding, maybe more theory, for example. A lot of the work we have been doing, specifically in these papers that we were talking about, but also more generally, a lot of it is we tried this, it worked, we compared it to that baseline, it worked better or worse, and so on, and very empirical. It would be nice to have a theory that allows us to generalize a little more, so that each problem that comes along is not wholly new. And of course, we build up intuition with the problems that we solved, but formalizing them more would be great. And of course, there is work along these lines. I just think there should be more.